Hello everyone. In this lecture, I would like to discuss matrices. Unlike determinants, a matrix is a square or rectangular array of numbers or functions that obey certain laws. Remember, in determinants, it's just a square. It has to be a square array of numbers or functions. But in matrix, it's square or a rectangular array. The numbers or functions in a matrix are called elements, and these elements are distinguished by two subscripts having the same indication as the two subscripts of an element in a determinant. For instance, if A is a matrix which has m rows and n columns, in this case A is written as this one here: A11, A12, A1n, A21, A22, A2n. Keep going here: AM1, AM2 until AMn. This is the shape of a matrix. It looks like this one right here. And the order of this matrix is m by n. So it's written like m by n. As a special case, if the matrix is a square matrix, in this case it's possible to construct a determinant from elements of the matrix arranged in the same way, which is called determinant of the matrix. And remember, this is only valid for square matrix. Some important notes we have to consider before going further in matrices. First one, here, the matrix elements cannot be combined. In determinants, we can solve the determinant and find the value for the determinant with a single number. But in matrix, you cannot get a single number. Let's start with laws and properties of matrices. The first property is equality. Matrix A equal matrix B if and only if each element of matrix A equal each element of matrix B. So matrix A equal matrix B if Aij equal to Bij for all values of I and J. This includes that A and B have to be the same order. As a second property of matrices is addition or subtraction. The operation of addition or subtraction of two m by n matrices is defined as C, it's a new matrix, equal to A plus minus B. So plus for addition and minus for subtraction. In such a way, here Cij equal to Aij, it's either plus or minus Bij for all values of I and J. Example, if A as a matrix, this one here, and B as a matrix, this one here. Now, as we can see here, A is 3 by 3 and B is 3 by 3. The question is find A plus B and find B minus A. Now, let's start with addition. So A plus B. To perform the addition in this one here, we actually add every single element of matrix A with every single element of matrix B. So in this case, A plus B equal to 2 plus 7. This is the first term. Minus 1 minus 4. 3 plus 3. 4 plus minus 2. 5 plus 5. 1 plus 6. 6 plus 1. 2 plus 3. 3 plus 2. As we can see here, we just added every element of matrix A with every element with matrix B. And this equal to 9 minus 5, 6, 2, 10, 7, 7, 5, 5. Now let's perform the subtraction. So B minus A equal to, same rule here, but we just subtract this from this, this from this, this from this, and so on. In this case here, 7 minus 2 minus 4 plus 1, 3 minus 3, minus 2 minus 4, 5 minus 5, 6 minus 1, 1 minus 6, 3 minus 2, and 2 minus 3. So in total, it's equal to 5 minus 3, 0, minus 6, 0, 5, minus 5, 1 minus 1. Let's define multiplication. The multiplication of a matrix A by a scalar quantity, let's name it alpha. Therefore, alpha A should be equal to A alpha. If we have two matrices A and B, in this case, two kinds of products are defined. Matrix product, which is AB, and direct product AB. This one here is defined as matrix product, and this one here is direct product. Note here that the matrix product is defined for conformable matrices, which means that the number of columns of A has to be equal to the number of rows of B. The number of columns of A must be equal to the number of rows of B. Let's have an example. If sigma 1 is defined as 0, 1, 1, 0, and sigma 2 is defined as 1, 0, 0, minus 1. Question, find sigma 1, sigma 2. Remember, this product is called matrix product. To perform the matrix product, let's do this. Sigma 1, sigma 2 equal to 0, 1, 1, 0 times 1, 0, 0 minus 1. We actually do this. We multiply the row with the column in this one here. So let's do this one here. 0 times 1 plus 1 times 0. And this is the first element of the resultant matrix. Now, the second element is the first row with the second column. In this case here, 0 times 0 and 1 times plus 1 times minus 1. Again, 1 0 with 1 0. So this row here with this, the first column here, 1 with 1 plus 0 with 0. And the last term is the second row with the second column, which in this case 1 times 0 plus 0 times minus 1. For that reason, the number of columns for the first matrix has to be the same number of rows for the second matrix. After all, this will be equal to 0 minus 1, 1, 0. Note, matrix product is not commutative except in special cases, and the associative law is valid in such a way AB, between parentheses here, times C, it's equal to AB with C. And there's also a distributive law, which also means matrix A times B matrix plus C matrix here, it's equal to AB plus AC. Now the direct product, and sometimes it's called tensor product, is defined as A, B equal C. In this case here, if A equal to A11, A12, A21, A22, and B equal to B11, B21, B12, B22, A, B equal to the whole matrix B should be multiplied by each element of matrix A, which means A11 times the whole matrix, which is B11, B12, B21, B22. And this is the first term here. And A12 should be multiplied by the matrix B, B11, B12, B21, B22, and this one here, A21, should be multiplied by B11, B12, B21, B22, and A22 should be multiplied by the whole matrix B, B11, B12, B21, B22. Or A direct product with B equal to A11. Now A11 should enter each element of matrix B. So A11, B11, A11, B12, A11, B21, and A11, B22. And same thing in here, A12 should be multiplied by each element of matrix B. So A12, B11, A12, B12, A12, B21, A12, B22. Same thing right here, A21 should be multiplied by each element of matrix B. So A21, B11, A21, B12, A21, B21, A21, B22. Same thing right here, A22, B11, A22, B12, A22, B21, A22, B22. 2. Two things we have to pay attention here is that A and B shouldn't be the same order, so it could be A 2 by 2 and B could be 1 by 2 or any order to perform the direct product. And note number 2, if A, for instance, is 2 by 2 matrix and B is 2 by 2 matrix, the resultant direct product of A and B will be 4 by 4, or in other words 16 elements. Example, sigma 1 equal to 0 1 1 0 and sigma 2 is equal to 1 0 0 minus 1. Find direct product sigma 1 sigma 2. In this case here, each element of sigma 1 will be multiplied by the whole matrix sigma 2. In other words, let's just do the resultant here: 0 0 1 0 0 0 0 minus 1 1 0 0 0 0 minus 1 0 0. And this comes from this 0 is multiplied by 1 2 3 4, so the 4 terms 1 2 3 4 zeros. Now 1 is multiplied by this one here, so 1 by 1 it's 1, 1 by 0 it's 0, 1 by 0 it's 0, 1 by minus 1 it's minus 1, and so on. It's good to mention that matrix division is not uniquely defined. Let's define the derivative of a matrix. Now, the derivative of a matrix is different from the derivative of a determinant. In matrices, if the elements of matrix A are functions of x, then the derivative of matrix A with respect to x is a matrix whose elements are the derived elements with respect to x. To understand this very well, let's have this example. To find the derivative of this matrix, we just apply the d by dx on each element of the matrix, and the resultant matrix will be d by dx for x squared, it's 2x, d by dx for 2x cubed, it's 6x squared, and this one here, right, 0, e to x, the d by dx for e to x, d by dx e to minus e to minus x, and d by dx for ln x, it's 1 over x. The situation here is quite different when deriving a determinant. Same rule is applied when we integrate a matrix. We actually apply the integration for each element of the matrix. Let's have this example. In this example, we would like to integrate each element of this matrix with respect to dx, and the integration will be a new matrix here. We will apply the integration on each element of this matrix. So integration 1 over x dx, it will be ln x plus c, and integration of 0 dx, it's equal to c2, this name it c1, and the third one it's e to x plus c3, and remember c1, c2, c3 are constants. This one will be x cubed over 3 plus c4 and x plus c5, and this one here 3x plus c6. And we can write the new matrix as the addition of two matrices, like this one here So this is len x, and this is C2, this is e2x, this is x cubed over 3, this is x, 3x plus, and remember, when you add two matrices, we actually add every single element of matrix A with every single element with matrix B. So this will be C1, 0, C3, C4, C5, C6. Let's define transpose of a matrix. A transpose of a matrix is actually constructed by interchanging the rows and columns of matrix A. So the resultant matrix is called transpose of A. So A, T, this is called transpose of A. And for instance, if A equal to 2 minus 1, 3, 4, 2, 1, then A transpose, in this case here, we interchange the row and make it column. So we change rows and make them column. So in this case here, it's 2 minus 1, 3, and 4, 2, 1. So rather than having two rows after a transpose, we will have 3 rows, and vice versa for columns. Instead of having 3 columns after transpose, we will have 2 columns. A very important note we have to consider here is A, B transpose is actually equal to B transpose A transpose. Remember, the order here is very important. It's AB, it's BA. AB transpose equal to B transpose A transpose. Let's discuss special type of matrices. For instance, the row matrix. So one here, the row matrix. From its name, it's a matrix which contains only one row. For instance, like this one here, A equal to A11, A12, A13, and A1n. This is called the row matrix. And as long as we have the row matrix, we also have a column matrix. So 2 here, the column matrix. Again, from its name, it's a matrix that contains only one column, like this one here, A equal to A11, A21, A31 until AN1. We also have the null or zero matrix. From its name, it's a matrix that all elements of that matrix equal to zeros. 3. The null or zero matrix. From its name, all elements of that matrix equal to zeros. For instance, A equal to 0, 0, 0, 0, 0, 0, 0, 0. This matrix is called the null matrix or zero matrix, and sometimes we can just write it like 0 rather than repeating zeros in this manner. So A equal to 0 for this type of matrix is acceptable. We should know that the null matrix has the property, if we add any matrix to the null matrix, the matrix remains the same, and if we multiply any matrix with the null matrix, the answer is 0. So A plus the null matrix, this equal to A and the null matrix multiplied by any matrix A, the answer is A multiplied by the null matrix, and the answer will be, after all, 0. There also be the unit matrix. For here, the unit matrix. From its name, this unit matrix, it's equal to 1 equal to only the diagonal equal ones and the rest of the matrix equal to zeros. And remember, this diagonal here, for this case, and this is called the unit matrix. Note here, this is not a unit matrix, not unit matrix. So this is called, in this one here, it's unit matrix. A good thing to know here, if we multiply a matrix by a unit matrix, then the answer will be the unit matrix multiplied by that matrix. So, for instance, the unit matrix multiplied by any matrix A, this equal to the matrix itself multiplied by the unit matrix. Now let's define the diagonal matrix. Now we defined here the unit matrix, and from its name, the diagonal elements are all ones. But if the diagonal elements are not ones, in this case it's called the diagonal matrix, like this one here. And this is called diagonal matrix. We should note here, very important, that the unit matrix and the diagonal matrix has to be square matrix. Like M by N matrix, it has to be M by M. So unit matrix and diagonal matrix should be square matrix. One last property of matrices is symmetric matrix. If the matrix is not changed under transpose procedure, then the matrix is said to be a symmetric matrix. In simple words, if A equal to A transpose, in this case it's called symmetric matrix. Example, A equal to 2 minus 1, 3 minus 1, 5, 6, 3, 6 minus 7, and A transpose, in this case here, equal to 2 minus 1, 3 minus 1, 5, 6, 3, 6 minus 7. Now, as we can see here, A is the same as A transpose. In this case, it's called symmetric matrix. We also can see that a symmetric matrix, if we just cover the diagonal right here, we can see that each element above the diagonal is the same as each element under that diagonal. Or in other words, the diagonal is making a mirror in this case here. So like -1, 3, 3, 6, 6. So this matrix here is called symmetric matrix. One interesting property of square matrices is that the trace. So trace the trace of product of two such matrices is independent of the order of multiplication. In other words, and this is always true even though AB does not equal to BA. Example, given the two matrices A and B, this one here, show that trace AB is equal to trace BA. So in this case here, before finding the trace, we should actually find the matrix multiplication AB and the matrix multiplication BA, then find the trace for both results and C. So let's find AB as a matrix here, equal to 1, 2, 3, 3, 1, 2, 1, 3, 2, multiplied by 2 minus 4, this is minus 4 by the way, 3 minus 1, 2 minus 3, 2, 1, 3. So the result will be, you just multiply the row with column, row with column, row with column. You just create the first row of the new matrix, which is 6, 3, 6. Then row with column, row with column, row with column. It will be 9 minus 8, 12. And the last one is 3, 4, 0. Now let's find BA equal to, so in this one here, 2 minus 4, 3, minus 1, 2, minus 3, 2, 1, 3, times 1, 2, 3, 3, 1, 2, 1, 3, 2. This equal to minus 7, 9, 4, 2 minus 9, minus 5, 8, 14, 14. If we look at AB matrix, it's different than BA matrix. Now let's double check the trace. The trace is the addition of the diagonal elements. So 6 plus minus 8, it's minus 2 plus 0. So the trace AB here equal to minus 2. Now let's check this one right here. Minus 7 plus minus 9, it's minus 16 plus 14. So trace BA equal to minus 2. Therefore, trace AB equal to trace BA. Let's define matrix inversion. Now, matrix inversion is defined as A minus 1 in such a way, this one here, A minus 1, this is called inverse of the matrix, equal to A inverse A, which is equal to 1. A inverse is defined as A cofactor transpose over the magnitude of the determinant of that matrix. So to find the inverse of the matrix, you have to find the matrix of cofactors, then take the transpose, and the result you divide it by the magnitude of the determinant of that matrix. Example, to find the inverse of the matrix, A equal to 3, 4, 1, 2, 1, minus 3, minus 2, 3, 1. We would like to find the inverse of that matrix. Let's find the cofactors matrix, which equal to, as in determinants, when you cover the first, for instance, row and first column right here, the cofactor for element 3 is this. 1 times 1, it's 1, minus 3 times minus 3, it's 9. So 1 plus 9 is 10, which is the cofactor for element 3. Now let's repeat the same procedure, but with element 4. You cover the first row and the second column. In this case here, the cofactor for the element 4 is 1 times 2 is just 2, minus 2 times minus 3, it's 6. So 2 minus 6, it's minus 4. And remember, the factor minus 1 to the power I plus j, in this case here, I in this case it's 1, and j in this case it's 2, minus 1 to the power 3, it's minus 1, minus 4, so it will be 4. Repeat the same procedure for the third element is 1, so the cofactor for that one it's equal to 8, and repeat the same procedure for element 2. In this case here it's minus 1, and don't forget this factor here, 5 minus 17 minus 13, 11 minus 5. So this is the matrix of cofactors. Now A cofactors transpose, in this case here we will transform every single row and make it columns. In this case here the answer will be 10, 4, 8, minus 1, 5, minus 17, minus 13, 11, 5. Now let's find the magnitude for determinant of the matrix equal to 3, 4, 1. This is the original matrix here, and you'll find the value for the determinant here, 2, 1, minus 3, minus 2, 3, 1. And when you solve this one here, it will be 54. Now, the inverse of the matrix, it's equal to A cofactor transpose over A, which equal to A in this case here 54, so 1 over 54 times 10 minus 1 minus 13, 4, 5, 11, 8 minus 17 minus 5. Now let's examine our result here. Let's find A inverse equal to 1 over 54, 3, this is the original matrix here, 4, 1, 2, 1, minus 3, minus 2, 3, 1. And you multiply by a inverse, which is this one right here. It's 10 minus 1 minus 13, 4, 5, 11, 8, 17 minus 5. So the answer after all, 1 over 54. When you multiply this one with this one, you will get 54, 0, 0, 0, 54, 0, 0, 0, 54. And after all, it will be equal to the unit matrix 1, 0, 0, 0, 1, 0, 0, 0, 1. Let's define orthogonal matrices. A matrix is said to be orthogonal if A transpose A equal to 1 or A transpose equal to A inverse. One of these conditions should be satisfied in order to call the matrix as orthogonal matrix. Example: in this example, determine which of the following is orthogonal matrix and which is not. Here's A and here's B. Remember, the orthogonality condition is A transpose A should be the unit matrix, or we can say that A transpose should be equal to the inverse of the matrix. Starting with A, so let's find A transpose will be equal to square root of 3 over 2 half 0 half minus square root of 3 over 2 0 0 0 minus 1. Now A transpose A, let's find this one here, square root of 3 over 2 half 0 half minus square root of 3 over 2 0 0 0 minus 1 times the original matrix square root of 3 over 2 half 0 half minus square root of 3 over 2 0 0 0 minus 1. Now when we do the matrix multiplication here, we will get 1 0 0 0 1 0 0 0 1. So in this case here, A transpose A equal to the unit matrix, and that condition is satisfied. For that reason, we can call the matrix A, which is this one right here, is orthogonal matrix. So A here is orthogonal matrix. Now let's double check the matrix B, this one here. So this matrix B here. So let's find B transpose, same procedure as before. So it's equal to minus 1 over 5, 0, 1, 1 minus 1, 0, 1 over 4, 1 over 2, minus 1 over 2. Now B transpose B equal to, let's just move this one here. So this is B transpose and this is B. When we multiply B transpose with B, the answer will be like this one here, 26 over 25 minus 1 over 5 minus 7 over 4 minus 1 over 5, 2 minus 1 over 4 minus 11 over 20 minus 1 over 4, 9 over 16. As we can see here, B transpose B does not equal to the unit matrix. Therefore, B is not orthogonal matrix. One of the important topics in quantum mechanics is eigenvalues and eigenvectors. So let's use matrices to identify the eigenvalues and eigenvectors. So the set of simultaneous equations Ax equal to lambda x in such a way A is a square matrix, which is n by n matrix. Lambda is a numerical constant known as the eigenvalue, and x is a column vector known as eigenvectors. So x here is defined as eigenvector. Lambda here it's eigenvalue, and A here is the n by n matrix. In a more general form, this equation right here can be written as A11, A12, A1n, A21, A22, A2n, an1, ann. This is the matrix A here times the x1, x2, x3 until xn. This will be equal to the eigenvalue lambda times the eigenvectors x1, x2, x3 until xn. And from this one here we get the set of homogeneous equations like a11 minus lambda. If we just move this part here, right here, this one here, so a11 minus lambda times x1 plus a12 x2 plus a1n xn, this equal to 0, and a21 plus a22 minus lambda right here, x1, x2 plus a2n xn, this also equal to 0. If we just keep going with this one here, so an1 plus ann minus lambda x, and this also equal to 0. If we set a determinant of coefficients, we will get a11 minus lambda a12 a1n a21 A2, 2 minus lambda, A2n, AN1, AN2, until ANN minus lambda. The whole determinant here, it's equal to 0. In a simple form, the determinant A minus lambda times the unit matrix equal to 0. And it's usually called characteristic or secular equation. Secular equation. To understand this very well, let's have this example. If we have a matrix A equal to 1, 1, 2, 0, 2, 1, 0, 0, 3, find the eigenvalues eigenvectors unit eigenvectors, which means the normalized eigenvectors. So we have this matrix here. We would like to find the eigenvalues, eigenvectors, and the normalized eigenvectors. So let's start with calculating the characteristic equation or secular equation. So 1 minus lambda, so this is A minus lambda, 1, 2, 0, 2 minus lambda, 1, 0, 0, 3 minus lambda, right here, this whole thing equal to 0. Remember, let's pick up the first column right here because it contains more zeros. So this will give us 0 and this will give us 0. So the only term that give us some values is this term right here. So 1 minus lambda times this with this minus this with this. So 2 minus lambda times 3 minus lambda minus whole thing is 0, and this will be equal to 0. From this one right here, lambda, it's either equal to 1 or lambda equal to 2 or lambda equal to 3. And these are the 3 eigenvalues for this matrix here. So 1, 2, 3. Now, in order to find the eigenvectors corresponding to each one of these lambdas, let's start with lambda equal to 1. Now we need to find the eigenvectors related to this lambda. In this case here, remember the rule, it's right here. Ax, it's equal to lambda x. Ax equal to lambda x. Therefore, from this one here, A, it's 1, 1, 2, 0, 2, 1, 0, 0, 3. This is A. And x will be x1, x2, x3, all equal to lambda in this case is just 1 times x1, x2, x3. When we multiply this row with this column, it's equal to x1. this row with this column, it's equal to x2. This row with this column, it's equal to x3. We will get three sets of equations: x1 plus x2 plus 2x3 equal to x1, 2x2 plus x3 equal to x2, 3x2 equal to x3. Upon simplifying these three equations, we will get this one here, x2 plus 2x3 equal to 0, because x1 cancel out with x1 here. x2 plus x3 is equal to 0, and 2x3 equal to 0. From the third equation, this one here, it's definitely that x3 equal to 0. And when we substitute x3 in the second equation, which is 0 in this case, so x2 will be equal to 0 as well. And for these equations, we cannot determine x1. Therefore, x1 is an arbitrary, and we choose x1 equal to 1. So the eigenvector for lambda equal to 1, the eigenvector will be 1, 0, 0. Now let's find the eigenvector for lambda equal to 2. So lambda equal to 2, use the same rule, ax equal to lambda x. So 1, 1, 2, 0, 2, 1, 0, 0, 3 times x1, x2, x3 equal to 2, which is lambda in this case, x1, x2, x3. Upon solving this, we will get the equations x1 plus x2 plus 2x3 equal to 2x1, 2x2 plus x3 equal to 2x2, 3x3 equal to 2x3. By deblocking to the third equation here, the third equation cannot be satisfied unless 3 equal to 0. So if we set x3 equal to 0, then x2 equal to x1. Then x2 equal to x1. Therefore, let's choose x2 equal to 1 and x1 equal to 1. Therefore, the eigenvector for lambda equal to 2 is 1, 1, 0. Now let's find the eigenvector corresponding to lambda equal to 3, this one here. Follow the same procedure. 1, 1, 2, 0, 2, 1, 0, 0, 3 times x1, x2, x3 equal to 3, x1, x2, x3. And from this one here, we will get the three set of the following equations: x1 plus x2 plus 2x3 equal to 3x1, 2x2 plus x3 equal to 3x2, and 3x3 equal to 3x3. From these three equations, if we set x3 equal to 0, so x2 definitely will be equal to 0 and x1 will be equal to 0. So there's no meaning for this 0, 0, 0 eigenvector. So let's choose x3 to be equal to 2. So upon choosing x3 equal to 2 and substitute back in these two equations, we will get x2 equal to 2 and x1 will be equal to 3. So therefore, the eigenvector for lambda equal to 3 is 3, 2, 2. Now, the last step is to find the unit eigenvectors or the normalized eigenvectors. So for lambda equal to 1, the eigenvector it's 1, 0, 0, and in this case here, the normalization will be equal to 1 over square root of x1 square, x2 square, x3 square. And after all, the x1 square is just 1, 0, 0. So the normalized eigenvector for lambda equal to 1 is 1, 0, 0. It's the same. No change happened here. Now for lambda equal to 2, the eigenvector is 1, 1, 0. To find the normalized eigenvector, we have to multiply this one here with 1 over square root of x1 square plus x2 square plus x3 square. Now in this case here, x1 it's equal to 1, x2 it's equal to 1. So the normalized eigenvector for lambda equal to 2 is 1 over square root of 2, 1, 1, 0. For lambda equal to 3, the eigenvector is 3, 2, 2. And in this case here, to find the normalized eigenvector, we have to multiply this one here with 1 over square root of 3 square, it's 9, 2 square, it's 4, and 2 square, it's 4. So the normalized eigenvector corresponding to lambda equal to 3 is 1 over square root of 17 times 3, 2, 2. Let's define reduction of a matrix to diagonal form, or in other words, it's diagonalization. If we have a square matrix A 3 by 3 and this square matrix A has 3 distinct eigenvalues, lambda 1, lambda 2, and lambda 3. The corresponding eigenvectors for lambda 1, lambda 2, lambda 3 is new columns C11, C21, C31, and C12, C22, C32, and C13, C23, C33. Now let's construct the new matrix C consists of eigenvectors as columns. So this matrix C, it's defined as C11, C21, C31, C12, C22, C32, C13, C23, C3, 3. And remember, this matrix C consists of the eigenvectors of lambda 1, lambda 2, and lambda 3. Now, upon multiplying the matrix C on the left by matrix A, we will get AC equal to A11, A12, A13, A21, A31, A22, A32, A23, A33. This is A times C, which is C11, C21, C31, C12, C22, C32, C13, C23, C33. Now the answer will be equal to lambda 1, C11, lambda 2, C12, lambda 3, C13, lambda 1, C21. We just multiply by eigenvalues, lambda 1, lambda 2, and lambda 3. So lambda 2, C22, lambda 3, C23, lambda 1, C31, lambda 2, C32, lambda 3, C33. Now, since A times C11, C21, C31 equal to lambda 1, C11, lambda 1, C21, lambda 1, C31, and similar results for column 2 and column 3. Therefore, A times C equal to C11, C12, C13, C21, C22, C23, C31, C32, C33 times lambda 1, lambda 2, lambda 3, 0, 0, 0, 0, 0, 0. Or AC equal to just C right here times the lambda 1, lambda 2, lambda 3. This is 0, this is 0, 0, 0, and both zeros. If we multiply both sides from the left by the inverse of the matrix C, we will get C inverse AC equal to C inverse C times lambda 1, lambda 2, lambda 3, and the rest are zeros. The answer will be just lambda 1, lambda 2, lambda 3. This is 0. And that's it. From the above procedure, we conclude that to diagonalize a matrix of the order 3 by 3 and the 3 distinct eigenvalues, lambda 1, lambda 2, and lambda 3, all what we need to do is to write these eigenvalues in the main diagonal and put all other elements equal to 0. So we just place here lambda 1, lambda 2, lambda 3, and the rest of the matrix is equal to 0. This process is called diagonalization. As an example for this diagonalization process, if we back to the previous example, when we find that lambda 1, lambda 2, lambda 3, it's equal to 1, 2, 3, so the diagonal matrix, example here, will be equal to 1, 2, 3, and we just put the rest of the matrix equal to 0. So this is the diagonalization for the previous example. Example, diagonalize the matrix using the invertible matrix C in such a way C inverse AC is diagonal. So the matrix here, we just find the eigenvalues and eigenvectors for this matrix. The eigenvalues, remember, it's equal to 1, 2, 3, and the eigenvectors for this matrix equal to 1, 0, 0, 1, 1, 0, and 3, 2, 2. These are eigenvectors. We just solved them in the previous example. So C is the matrix of the eigenvectors, which is 1, 0, 0, 1, 1, 0, 3, 2, 2. And let's find C inverse right here equal to, remember, the inverse of the matrix, it's equal to C, the cofactors transpose over the magnitude of the determinant of that matrix, which equal to half 2 minus 2, 1, 0, 2 minus 2, 0, 0, 1. Now let's find C inverse AC, which equal to half 2 minus 2 minus 1, 0, 2 minus 2, 0, 0, 1 times 1, 1, 2, 0, 2, 1, 0, 0, 3 times the original C matrix, 1, 1, 3, 0, 1, 3, 0, 0, 2. Upon multiplying these matrices here, the answer will be equal to half 2, 0, 0, 0, 4, 0, 0, 0, 6. And if we pick up 2 as a common factor and cancel out with this half here, the answer will be 1, 0, 0, 0, 2, 0, 0, 0, 3, which is the same result as obtained in the previous example. Let's define the Hermitian matrices and unitary matrix. The Hermitian matrix, or sometimes it's called self-adjoint matrix, is a square matrix which has the same as the transpose of its complex conjugate. So if A is a Hermitian matrix, one can write A here equal to A complex conjugate transpose, which equal to A complex conjugate transpose. This is called Hermitian matrix, and A complex conjugate transpose sometimes defined as a dagger, and this is called adjoint matrix. From this definition, we can see that the symmetric matrix is actually a special case of a Hermitian matrix when all the elements are real. Therefore, a matrix U is said to be unitary matrix if U inverse equal to U self-adjoint matrix. If this condition satisfied, this is called unitary matrix. As a matter of fact, this matrix is very important in quantum mechanics, and obviously the orthogonal matrix A inverse equal to A transpose is just a special case of unitary matrix when all elements of A are real. In addition, the similarity transformation is defined as, by this relation here, A prime equal to T A T inverse, and if a unitary matrix is used in a similarity transformation, then it's called unitary transformation, and it takes the form A prime equal to U A U inverse or U A U dagger. Note number 1. The eigenvalue of a Hermitian matrix or symmetric real matrix are real. As another note, the eigenvectors of a Hermitian matrix or real symmetric matrix belonging to different eigenvalues are orthogonal. Let's have example. Given the matrix, this one right here, find the eigenvalues, then find the normalized eigenvectors. After that, show that these eigenvectors are orthogonal and write the diagonal matrix. Starting from the secular equation here, 1 minus lambda, this one here, you just subtract from the diagonal lambda, so it's equal to 1 minus lambda, 0, 6, 0, this one here, minus 2, like this one here, 0, 6, 0, 6 minus lambda, this equal to 0. Upon solving this one here, 1 minus lambda times minus 2 plus lambda times 6 minus lambda plus 36, 2 plus lambda, all equal to 0. And from this equation, we will get lambda equal to minus 2 minus 3 and 10. Now let's find the eigenvector corresponding to lambda equal to minus 2. So for lambda equal to minus 2, then 1 plus 2, 0, 6, 0, minus 2 plus 2, 0, 6, 0, 6 plus 2 times x, y, z equal to 0. You will get from this one here 3x plus 6z equal to 0, 6x plus 8z equal to 0. If we set in this one here x equals 0 and z equals 0, so x equals 0, z equals 0, then choose y equal to 1. So the eigenvector for lambda equal to minus 2 is 0, 1, 0. Following the same procedure for lambda equal to minus 3, right here, you will get 1 plus 3, 0, 6, 0, minus 2 plus 3, 0, 6, 0, 6 plus 3, times x, y, z equal to 0. 3 set of equations for x plus 6z equals 0, y equals 0, and 6x plus 9z equal to 0. Obviously, y equals 0. We cannot choose x or z equal zeros. So if we choose z equal 2, then x equal to minus 3 and y equal to 0. So the eigenvector for lambda equal to minus 3 is minus 3, 0, 2. Now let's find the eigenvector related to lambda equal to 10. Following the same procedure, 1 minus 10, 0, 6, 0, minus 2 minus 10, 0, 6, 0, 6 minus 10, times x, y, z equal to 0. Upon solving this, we will get 3 sets of equations. Minus 9x plus 6z equal to 0, minus 12y equal to 0, 6x minus 4z equal to 0. Now from this one here, y equal to 0 and 3x equal to 2x, and the eigenvector for lambda equal to 10 in this one here is 2, 0, and 3. Therefore, the normalized eigenvectors are 0, 1, 0, and 1 over square root of 13 minus 3, 0, 2, and 1 over square root of 13, 2, 0, and 3. And remember, to find the normalization factor, we should multiply the eigenvector with 1 over square root of x squared plus y squared plus z squared, and this is called normalization factor. To prove that the eigenvectors are orthogonal, if we multiply two eigenvectors together and get 0, then they are orthogonal. So 0, 1, 0, if we multiply it by minus 3, 0, 2, there's no need for the normalization factor in here. If we multiply this with this, the answer is 0, and 0, 1, 0 times 203, and it's equal to 0 as well, and minus 3, 0, 2 multiply by 2, 0, 3, and it's equal to 0. Therefore, the eigenvectors 0, 1, 0, minus 3, 0, 2, and 2, 0, 3 are all orthogonal. The last thing here is write down the diagonal matrix. Therefore, minus 2, 0, 0, 0, minus 3, 0, 0, 0, and 10. Remember, to write the diagonal matrix, we write on the diagonal lambda 1, lambda 2, and lambda 3, and the rest of the matrix are zeros. That's it. Thank you for watching.